this afternoon will be Alexander Beilinson, who has had to overcome many difficulties on the dark and worldly road from Chicago to Cambridge, and also improving the theorem that he's going to tell us about now.
Thank you. Thank you for the invitation. I will speak about one problem which was posed by Pierre Deligne back in 1984, and it looks like this. Suppose that we have a complex curve over C, and suppose that we have M, let it be a holonomic d-model on X, so it is you can think of it as outside of finitely many points. It is a vector bundle with a connection, and it extends in some way to the points. Then we can consider the Durham cohomology of X with coefficients in M, and it is defined purely in a purely algebraic manner. On the other hand, so we can do it whenever X is defined over some field of characteristic 0, not necessarily C. On the other hand, over C, we can compute it in a topological manner. We can use classical topology on X to define the Durham, to consider the Durham complex of M. So we will view it in a classical topology, and then, well, it's known that the thing is perverse sheaf. So I put it in degrees -1 and 0, and viewed as a perverse sheaf of complex vector spaces, I will denote it by B of M. Certainly the usual, so this is cohomology of Durham of M viewed in Zariski topology, and we can compute it in classical topology, and we get the beta cohomology group. Okay, and certainly the two are the same. So the Durham and beta cohomology, but again they have a different flavor. They have different nature. This is purely algebraic, and this is topological. And these natures can be tested in the following manner. So we can view two types of rational structures. So a Durham type would come if, for example, X and M would be defined over Q, and then this complex vector space will acquire the corresponding rational vector rational structure. On the other hand, we can consider B of M and ask it a Q rational structure on this perverse sheaf of complex vector spaces, and if we have such a Q vector structure, then certainly according to this formula, the beta cohomology will get rational structures, and and if we have both, you will have a same complex vector space. Let's define this isomorphism by rho. We'll have same complex vector space with two different rational structures, and we can, for example, assign to the thing a number, namely, if you wish, just computing the determinant of rho in two rational bases, and this number will be defined up to a rational number. So we will get a well-defined element of this group, and we can ask how to compute this number. And Deligne, well, this number, in a sense, it's analogous to determinant of Frobenius cohomology for variety characteristic over a finite field, and the latter can be, there is a product formula which expresses this in terms of product of local epsilon factor, and then you ask if there is a similar formula for this number. If it can be naturally written as a product of local factors. Well, and I recall that the usual epsilon factors, they depend on extra data of an additive character. And, well, if you play over a finite field, global additive character is essentially the same as non-zero, well, rational differential forms. So we would like to have a formula of that type where nu is a rational one form defined over Q, and the product, so this should be x is a point of x, and we should have such a formula whenever, this number should be trivialized outside, where if x lies outside of singularities of M and singularities of nu. And one can ask if there is such type of formula, how to define the local factors. Actually, Deligny also suggested a format for such, to obtain such product formula, which somehow makes it more comprehensible. Namely, the format looks like this. So first, well, it is essentially, it says that such a formula should come from, from the decomposition of the determinant of the cohomology on the local level. And the format, the conjectural format, looked like this, that we would like to have whenever we have such a situation, and we would like to have locally defined epsilon factors. And this would be just lines. So if we have a point in X and a non-zero meromorphic form on a neighborhood of X, we should be able to assign to it two lines. And by line, I mean a one-dimensional complex vector space equipped with a grading. I recall that the determinant of cohomology is naturally has a grading equal to the Euler characteristics. Considering this grading is important when you consider how cohomology behaves when we consider direct sum of atoms. So the second thing is that this line should have, just as global determinant of cohomology, they should have a similar nature. This line should be defined in purely algebraic manner, and this should be defined in purely topological manner, so that if we have rational structures in both types, then we should have respective structures on the corresponding lines. Well, and the third thing is that we should have the product formula isomorphism. If our, so this data were of purely local nature, and if X is compact, then we should have a product formula isomorphism between the tensor product of the RAM epsilon factors, and I forgot to say that they should be, this line should be canonically trivialized if x lies outside of singularities of m and nu. And same should, so this is the RAM isomorphism, and same, there should be similar Betti picture. And given such, so if we manage to produce such a data, then we will immediately be able to deduce product formula in the situation when the corresponding rational structures would be present. And sorry, I did not say that this isomorphism should have algebraic nature. So if it is defined over Q, and this should be an isomorphism actually of Q lines, and same here. And sorry, I'm sorry. So this this decomposition, and the last part of structure, I'm sorry, should be the identification of the corresponding epsilon lines. Let me denote it by eta, and this is and this isomorphism should have purely local nature, and the key property of this data should be that in case of compact curve, this identification should be compatible with rho. So if we have here so here we have the determinant of rho isomorphism, and here we will have the tensor product of isomorphism eta. And again, we immediately get from this picture on the level of lines, we get numbers. The corresponding rho epsilon would be, if we have rational structure, will be just this isomorphism computed in a rational basis, and this compatibility will produce the global formula. So actually, such a construction was partially done by Deligne back in '94 in case of when M has rank 1, and then it was extended to a little bit special case of rational structures compatible with structure of irregularities, irregular singular points, in the work of Bloch, Deligne, and Eno several years ago. Well, and also in the case assuming that M has virtual rank 0. And I will sketch a proof of existence of this format in a general situation. So I will begin with I will try to explain what epsilon factors actually form. Certainly, if we fix M, then we can move x and nu. If we fix M and the curve, we can move points and we can move nu. And certainly, if my curve was compact, then the tensor product of all epsilon factors will remain the same. It would be the determinant of cohomology. And the structure I will try to explain. So first I will just say kind of axiomatic structure for epsilon factors. Will be an attempt will formalize the following property. So again, for compact curve, we see that the tensor product of all epsilon factors remain constant. But suppose that we move them a little bit. Then certainly the singularities of nu themselves, so the place where epsilon factors are non-trivial. Will move, but still they will cluster around if we move a rational differential form, then the singularities of moved form will somehow cluster around the singularities of the initial form. And the local structure on epsilon factors that I will explain is a formulation of the property that the corresponding global isomorphism actually global constancy of the product of epsilon factors come for the reason that, for the local reason, that if you move a little bit of differential form, then the tensor product of epsilon factors of a nearby differential form just canonically identifies with epsilon factors of the initial form. Such a structure, I will explain it in the drum setting, but it's very general. You can formulate it in topological setting or in a tile. So let me call it factorization line. And we will see that it's essentially a reformulation of a geometric class field theory. So our initial data would be a curve x. Well, you can think it over complex numbers, but it could be any field of characteristic 0 if you wish. A finite subscheme T inside of x. And T will be, when M comes, this will be the position of singularities of M, but computed with multiplicity equal to, to the order of pole of the connection on the determinant of M. So that's a datum. And I would like to define the notion of factorization line on such a pair. So to introduce it, let us, I will need also an extra, well, this will be a twisted factorization line. So, and they will be twisted by the canonical bundle. But inside of, when I formulate it, it's more reasonable to pick a just general line bundle on X. Now, to such a datum, I will let's assign a space. So the space will be. So first we make. I will consider the space of divisors on X, and by space I will mean just something which has points with values in schemes. So I don't ask it to be actual scheme or something like this. So I will consider the divisors over X. And so an S point of the space is an S family as a relative Cartier divisor, which is finite over S. So these are. Okay. Another space which is actually a scheme will be the scheme of subsets of T. So it says points are idempotent functions on T times S. And now the next scheme, let me denote it by D. And this will be a subspace in divisor times 2 power T, which is consists of all pair D and C with the property that if I will intersect all points of intersection of D with T lies inside of the support of C. So if I have an element C here. So it's and then its support I will denote it by TC. Okay. It's a little bit formal definition, but it's worth to formulate them. And the last space will be the diamond which projects onto D, and that's a space of all triples D, C, and there will be also nu, where D and C are from here, and nu is a trivialization of K restricted to the following subscheme. I consider TC union with the support of D. Well, let me denote it as model D. And the support I understand as a reduced closed subscheme. Okay, so that's all formal data. So now the first kind of objects I would like to consider is invertible de Rham local systems on this vector space. These are key objects. And I will call them de Rham lines, and I will assume them to be graded in order to be able to consider tensor product with a corresponding commutativity constraint. And by definition, so this is not a variety, but still you can consider points with values and varieties. And, so as usual, in this manner, I can say what is a de Rham line on such a space. So the de Rham lines, they form a Picard groupoid. So whenever I have such S point of Denable, I will have a de Rham line on the space of parameters. Well, and first lemma that I want to formulate is this, that suppose that X, so here X need not be proper, but now suppose that X is proper. Well, then we can consider there are special, we can consider the space of rational sections of K. And to each such rational section, well, formulate lemma a little bit later. Non-zero rational section of K. Now, lemma. This is again naturally a space, but the space is, well, it is of contractible type. Namely, the claim is that there is no functions on the space, but constants. And every line or de Rham line on the space is automatically constant. So, so by the first, so therefore we see that the RAM lines are just the same as lines over a point, and therefore if we have, there is a natural map. Notice that namely if we have a rational form, then we can assign to it a triple minus its divisor. Well, we take whole at C, so it will be C will be equal to 1, and then here we'll have nu itself restricted to its divisor and T.
Which sort of object is that x case? That x case, is this a big infinite dimensional scheme?
Well, it is a space. Again, you can consider a point, an S point of such a space will be a rational differential form on the product, which is non-zero on every x times closed form, which is defined over x times closed point. It will be defined on an open subspace which intersects every closed fiber. So that's a space. Okay. So the space maps naturally here, and therefore if I have any the RAM line, I can pull it back to the space, and that will be constant. It will not depend on a point. So therefore, in case of proper curve, I can define just if I have E side of, so that's corollary. I can assign to it, well, let me denote it just E of x, and this by definition will be E taken over such a thing that corresponds to nu. Let me write it E nu just, and this will not depend on the choice of a global rational form. Okay, so we have a map. So for compact curve, if you wish, we have a morphism of Picard groupoids, which are assigned to every line on the space, assigned just a usual global line. Now, that's a part of a structure that I would like to consider. Now, definition. So I would like now to consider factorization lines. So suppose that we have E which sits in this Picard groupoid. Then I define a factorization structure on E in the following system of isomorphism. So suppose that I have a collection of points, just a finite set of points of as points of the space. Then I can say when they are disjoint. So by definition, this means that the corresponding subschemes, the subschemes are mutually disjoint. Okay. So for disjoint, for a finite collection of disjoint points, any finite collection of disjoint points. Now we would like to have the structure assigns to it an isomorphism between the tensor product of these lines and E, which is assigned if you have a disjoint family of points, we can form their union. So we consider the sum of the divisors, the sum of the idempotents, and just nu formed by the collection of nu alpha. So the product of C And what we would like to have is to have a factorization structure as a collection of such isomorphisms. So if you wish, if we have a point of the space which is decomposes into disjoint union of several points, then we will have a tensor product of isomorphism. And I would like the data of this isomorphism be transitive with respect to further decomposition. Well, this will be lines equipped with factorization structure certainly it has multiplicative nature, so they form themselves a Picard groupoid. Let me denote it in this manner. X, T, there will be also T. So that's the Picard groupoid of factorization lines. The important property of the structure is that factorization lines have local nature. Certainly the space D diamond itself, it is not local. You have its points are comprised by several points of a curve, and therefore, though if I have an open subset of X, I can restrict on it if I have just the RAM line on D diamond for a whole curve, I can restrict it and get lines on open subsets. But this sort of presheaf structure, you cannot glue them together. But factorization lines, they have local nature. They can be glued. And that's a simple exercise. So that's an important point. Have local structure. And the key fact is that actually you can describe very easily this Picard groupoid of factorization line. It has very concrete description. Let me formulate it quickly. This description is essentially the geometric class field theory. Pardon? Suppose that you have E which lies on this a line on this space. Now, a factorization structure on such E is a datum of factorization isomorphisms. Each factorization isomorphism comes whenever I have a disjoint family of points, and then I should have an identification of the corresponding of the tensor product of the lines of each point with the one for their union.
Yeah, but I'm wondering about the top. There you are defining EX to be that.
This definition.
That is a map. Actually.
Okay, so here is the definition. So we have a map from this space to this. So if I have a line on this space, I can consider pull it back here. And here it becomes constant. So it is the same as a usual line. So if you wish, if I have a point, just usual K point, C point here, I can consider the corresponding E over this point. And this will not depend on the choice of the point of the space. So I denote it, so I do not write extra new. Okay. Now let me say briefly how one describes this Picard groupoid. So in this description, you will see that it's purely local. Maybe before I give this description, let me say that the epsilon factors I will be looking for, that the RAM and beta, the RAM one will lie exactly in the corresponding category, and in these terms, the global product isomorphism will be simply, so if I will So what I will be looking for in case of the RAM situation, I will be looking in epsilon the RAM of M sitting here, and the product with the product isomorphism formulated like this. So we consider the corresponding global line M of X, and this should be identification of it with the determinant of the cohomology. So that's for future. Okay. Now the description of and here I'm sorry, K will be equal to the canonical bundle. Now the description of the category. Well, so first, if we live outside of T, then inside of the diamond lies, well, there lies a natural subspace which is formed by pairs. Well, if we live outside of T, so C will be equal to 0, of where D is a simple divisor of degree -1. And this subspace so will be is the same as consider well, nu will be an element of, then it will be a section of K which has a pole of order 1 at a point. And this is the same as an element of the fiber of K tensored by inverse line bundle to omega. So inside of D lies the space of the line bundle K tensor omega x tensor -1. The space with removed 0, so invertible elements here. Now we can, so therefore, if I have an object here, I can restrict it to the space, and effect, which is not very difficult to prove, is that what we will get here, we will get a Daram line, that it will be monodromic along the fibers, and moreover, the monodromia will be equal to ±1. Or if you wish, if I take the tensor product of this restriction, then it is a pullback of a Daram line on x minus t. Moreover, the monodromy itself along the fibers equals to -1 power the degree of, I recall that here the lines has degree, and it will be equal to -1 power the degree of the line. So consider, let's denote by in this manner of x, t, and well, let me denote it just 1 here. So by definition, it is the Picard groupoid of the corresponding object. So we consider Daram lines on the space with this property that it's monodromic along the fibers of the projection with monodromy equal -1 power the degree. That's one property. But here also comes t. And what I would like to have is that if I consider the tensor square of my line, so it comes from a Daram line on x minus t, I would like that the poles of the corresponding connection at points of t will have order less or equal than the multiplicity of t. Okay. So two properties. One is the control of the singularities, and second is that it's monodromic with this ±1 monodromy. So essentially, if you wish, it's a twisted form of the Picard groupoid of line bundles on x minus t, the Daram line bundles on x minus t with order of pole let t less or equal than the multiplicity of t. Now, the claim is that if I restrict, so if I have an object here, if I restrict on this subspace, then I will get come into this Picard groupoid. So, I will formulate now a general theorem, but a particular case of this would be that if T is empty, then this is an equivalence of the Picard groupoids. If T is not empty, I should add extra data of T, at T. Namely, suppose that for each point B, well, B alpha, let's write T as a collection of points B alpha, and suppose that I have any non-zero rational form or a Laurent power series nu alpha near B alpha. Then just let's fix it. Power series section of K, sorry, of K near X alpha. Then what I can do, I can just restrict, it defines naturally a point of this divisor with C supported at B alpha. So I can pull it back, and then I will get a line just over a point. And the claim is that it's just an equivalence of Picard groupoids. So the data is local system of lines outside, and just a line for each of the points. And I should say that, again, if K is the canonical bundle, then this space is trivial. So I can just pull back so it's canonically trivialized by forms of residue 1, and I can pull it back, and then I can delete this twist. Case when K is omega x. Delete this twist, and I will get an equivalence. So that's a description. Now let me pass to, quick story. So now a system. So let me define what is a system of epsilon factors. Again, my problem is analytic, and certainly everything that I told here can be formulated in analytic situation. And I should compare two analytic. I'm willing to compare two analytic line. One, the Daram one. Another is Betty. And let me define. What is for us will be a theory of epsilon factors. So we'll consider a data like x, t, m. So x is a complex curve, t is finite subscheme, m is a holonomic d-model which is non-singular outside of t and whose order of pole of determinant of connection is less or equal than multiplicity of t at a point. And then we want to assign to such a data a factorization line on xt twisted by omega. Now what we want to have is first, just general compatibility. So first, we would like to have that the thing will be compatible with filtrations on M. If we have a filtration, then we want to have identification of epsilon of M with standard product of epsilon of gar alpha. Here. this type of, so that's the first constraint. Second constraint will be, I will not formulate it precisely due to the lack of time, that if I have finite projection, then I will have projection formula. And the third thing is, what we are looking for is in case when X is compact, I should have the product formula isomorphism. So this is a product in a sense, as I explained there. So we should have such an isomorphism. Well, and that's all for well, and the zeroth point would be that if I have if such a datum varies holomorphically and in a way that the singularities of M at T, so first T varies, well, it's a finite subscheme, but there is no ramification. The points do not glue. So one condition, and ask also that the singularities of M do not jump. Well, there is a corresponding notion as theories of, well, in this situation, I would like that E of M would vary holomorphically. And if I have a flat connection on the whole space, so if you wish, if my deformation is isomonodromic, I would like to have well, Gauss-Manin type connection on E, and I would like to have the compatibility with these notions. In particular, in global situation, I would like to have compatibility of this connection with the determinant of the Gauss-Manin connection. So that's the theory of epsilon factors. Now, there is one extra compatibility that takes time to formulate, and I will not do it. But that's a pure compatibility. It's not extra data of constraints, but pure compatibility with quadratic degenerations of curves. If you have a quadratic degeneration, then you can formulate what it means that the theory of epsilon factor on the in the limit on the family tends to the epsilon factors on to the picture of epsilon on the limit. I don't have time to formulate, but again, it's a pure property. Now, a key theorem here is that if you look that epsilon factors, certainly they do not form a Picard groupoid. So here, this condition, you cannot tensor product of two epsilons, but it forms, well, it is a GERP. It is, if we put here, instead of this isomorphism trivialization, we will get a Picard groupoid, and the theories of epsilon factors form a tensor over this Picard groupoid. And the key property is that this Picard groupoid is actually trivial and has group of automorphism of any object equal to Z. Another way to say it, that if we have any two systems of epsilon factors, then you can identify them canonically up to a power of a canonical automorphism. This theorem, I do not have time to explain it, for I would like to give a very short sketch of the construction of the Raman-Bethe situation, but it is not, there is one serious ingredient in this theorem. So you proceed, essentially the proof proceeds as follows. So first, you would like to see that the theory of epsilon factors is completely for any, so it's a local thing, so we should define them at essentially at singularities of M. And since if we have a disk, we can compactify all the pictures so that this disk, and extend our thing essentially canonical to P1, so that at infinity the singularities will be regular. And in this manner, everything is defined by regular singularities. the picture with regular singularities, if you look about quadratic degeneration, then you will see that if you consider the values of E, I'm sorry, so now should have said that I consider the ratio of two epsilon factors, so the objects of this Picard groupoid here, and they have actually degree 0, it's easy to see. Well, then if I will consider epsilon factors for M with regular singularities of rank 1, then such a regular singularity is determined by its monodromy. So for each value of monodromy, we have with the corresponding line epsilon. And you can see that using this compatibility with quadratic degeneration, that this is naturally that this data is an extension of a copy of C star, the value of monodromy, by C star, this E of M. And that's a group extension, it's a commutative group. And each such group extension is trivial. And in this manner, you identify all local epsilon factors. But it's a non-trivial fact that you will have now compatibility with global isomorphism. And this fact comes from a quite non-trivial theorem from Teichmüller's theory due to Goldman and Pickrell and Xia, which tells that if, so the theorem tells that if I consider pointed surface, if I consider surfaces with boundary of genus maybe larger than 3, and I consider local system of given rank maybe larger than 2, don't remember on it, then and consider unitary local systems, then you will have the action of the Teichmüller group on the space. And the claim is that this action is ergodic. And this fact is used here to see that the discrepancy between the local identification and canonical global identification, it is a holomorphic function on the corresponding parameters. And this function on the spaces of local systems. And this function is constant on the real part, which corresponds to unitary local systems. Well, and therefore it's constant, and the discrepancy actually, this means that it has purely local nature. It depends only on local behavior of monodromies. And then, well, then you essentially you get it. Well, now for the remaining 7 minutes, let me just let me sketch actually, probably I will explain, it's less known, the RAM part, how to construct the RAM epsilon factors. Actually, it was done already by Pierre in 1984. Let me just explain how you define the Bates factors. So in order to and the construction is it has two simple components. So suppose that we have our X. Well, it could be actually any real analytic manifold. Then we can consider subanalytic relatively compact subspaces of X. Let's call it C of X. And this is naturally a Boolean algebra. On any Boolean algebra, we can consider measures, certainly, and less common, we consider measures with values in any Picard groupoid. If the Picard groupoid is discrete, this is the usual notion of measure. But actually, we can consider measures with value in any Picard groupoid, in particular Picard groupoid of lines. And the notion, and the, now, so this will be a rule which assigns to any element of Boolean algebra the corresponding line. And the property of measure is now not a property but a constraint. If I have some C which is disjoint union, which is partitioned into subsets C alpha, then I should have an identification of tensor product of C alpha with lambda of C. And the identification should be transitive. So that's the notion of measure. Now, the first remark is that if I have a constructible sheaf f on X, then it defines you naturally a measure on, with value in the Picard groupoid of invertible line, and defines you a measure on C of X. And by definition, so let's call it lambda of f, and the measure of C, it's if C with so it's well, so the key thing is that if C is locally closed, then I can consider I can restrict f to C. Well, let me restrict it in an upper Schrick sense and consider the corresponding cohomology. These are finite dimensional vector spaces, complex of finite dimensional vector spaces, and then I can consider the determinant. Now, if and the fact is that if I have certainly if I have a flag of locally closed subspaces, well, relatively closed, then we'll have filtration on R gamma, and that produces you the identification of the determinant of cohomology with tensor product. And the claim is that this kind of constraint extends in a unique manner to a measure. That's a simple property. So the first thing is that you have a measure, that this formula defines you a measure on C of X. But this is, and what we want to do is to be able to compute, if I have, for example, my X as a compact curve, is to compute lambda of f, just the measure of the whole space X, in local terms. But to do it, I need a differential form. Now, how the form comes? Now, suppose that we have the following thing, that we have a family of proper cones in tangent spaces to my X. So at each point, I have a triangle with angle less than 180 degrees in the corresponding tangent place. Yes, let's. Actually, it can be spelled out in higher dimensions, but it takes longer time. X is a surface. Now, this defines you some ideal inside of, sorry, not an ideal, and subalgebra in C of X. Namely, it is generated, subalgebra generated by special open subsets, special locally closed subsets, where I call a locally closed which of the following types, that locally there should be difference of two n-invariant closed subsets. And invariance means that I consider n as a group of semi-group of infinitesimal movements. So, for example, if n looks like this, then certainly if I will move, then the triangle itself will be such a subset. Also, this will be an invariant subset, and the difference will be kind of a rhombus. That's a typical subset which lies in I. Also, I want them to be small in some sense, and I don't want to explain it for the lack of time. So, and the fact is that if the key fact is that if I have a local system f on X, then the determinant of cohomology of any C with this property from I is trivialized. And this trivialization extends to a trivialization of the restriction of the trivialization of the measure on this subspace. That's a very general fact, which is essentially it goes back to at least a book of Kashewara and Shapira. Now, now my situation is that I have my surface, and I have f, which is a constructible sheaf, so it has some singular points. And also I have a differential form, nu. Well, let's, and it has also some singular points. So outside of So I have finite collection of points such that my F is a local system outside of these points. And I have a non-zero differential form, and I need just topological differential form, which will be the real part of the holomorphic form nu that I considered there. Now I can take for n just any family of cones on which this real part of nu is negative. Okay? Then outside of this finitely many point, let u be x minus this special points. On this nu, I have my n, and therefore I have the corresponding I. Now I want to consider that's a Boolean subalgebra. I can view it inside of C of x. And I want to enlarge it a little bit. Namely, I want to consider its normalizer inside of C of x. And also, only those elements of normalizers, the subsets which have property that their intersection with S equal of maybe of their closure is the same as intersection of their interior. So this means that if I have a subset C, that if I have a point, then either the set C contains a neighborhood of a point, or its closure does not contain the point. Now, it's easy to see that, so this will be a subalgebra in which I is a normalizer. Now, it's easy to see that just essentially from the definition that the quotient of this larger algebra modulo I, if I assign C the intersection of C with S, then this larger algebra, then certainly I will go to the empty set, and actually it identifies the quotient of the corresponding Boolean algebra modulo I with the algebra of all subsets of S. So therefore we have a measure on the whole C of x. We restrict it to the subalgebra, so C of n, let's call it C of Sn inside. So we restrict lambda to this space, and according to this property, we have trivialization of this measure on the ideal. Therefore, we get a measure on the quotient algebra, which is the algebra of finite subsets of S.
CSS is normalized.
Pardon? Yes, it normalizes the ideal. And therefore, we get a measure on the quotient. And again, the quotient is Boolean algebra of the finite subset of S, so we have a measure on S. Or which is the same, we know the measures of points. And these measures of points are exactly the epsilon factors. If so these are epsilon factors that correspond to nu at this point. And the product formula that if x is compact is just a property that the measure of the whole x is the same as product of this measure by the points. And that's a measure property because we compute it by projecting to the quotient. And that's a factorization. So that's essentially the construction of the beta epsilon factors. Maybe the last remark is that, well, the round factors, again, it's an old construction of Pierre, and I will not explain it since I'm out of time already for 2 minutes. But the only remark is that all these constructions are very much non-motivic. And that's a mystery of the story. For example, I have no idea how to define geometrically a theory of epsilon factors in this sense in elliptic situation. So that's it.
Where do the gamma values come?
The gamma values come if you compute the corresponding identification for just rank 1 things. And the fact that you get gamma values is almost trivial from the characterization of gamma function essentially position of its poles and the multiplication formula, which corresponds here to projection compatibility with projection isomorphism. So it defines gamma function up to multiplication by exponential, and this exponential corresponds to the fact that this theories of epsilon factors, they form a Z-sharp. So this is this canonical isomorphism which comes.
Yeah, in this final construction, how do you get this constructible sheaf F?
That's B of M. So I need to assign to a holonomic D model epsilon factors. So I first pass to B of M. The construction should be topological, so it should recover epsilon factors from a constructible complex B of M.
This formula is analogous with the one with Frobenius on variety. Can you write it precisely?
I cannot, because I do not know. That's my last phrase was that I do not know how to make the corresponding constructions. There is the proof of the product formula for the determinant of Frobenius on cohomology, which is this beautiful Fourier argument by Lamont. It is. I do not know if you can use it to get the picture in a similar formalism. The reason that what Lamont gets, he has his input is which is not a rational, global, say, rational form or local rational form, but it's actually a form which is a differential of a function. And the output is also, it's not a graded line, but actually a vector space whose determinant is the epsilon line. And certainly in this setting, you can get only lines using forms. So somehow he starts from a finer data and gets a finer output. It suffices to prove the formula on the level of numbers, but I do not know if it suffices to construct such a story.
So let's thank Alexander.